Hi, everybody. Thank you for coming back from lunch. My name is Janine Captain, and I'm here representing the Viper mission team to share with you some of our recent advances and just tell you where we are with our mission. We're going to build on the exciting plans of this morning, and I'm going to say that just 2 decades ago, or just to date myself when I started at NASA, the moon was a very different place. And my first project was actually trying to find a little bit of water in a big hydrogen background. And so we thought the moon was very dry. There were a few people that said, well, maybe the hydrogen is in water, but we didn't have any proof at that time. So, of course, we all know that we continued the hunt for lunar volatiles, and we discovered that the hydrogen is indeed in water ice. So we discovered and confirmed that water ice exists at the lunar poles, at the South Pole. And so now that we know that the water ice exists there, the next question is, how is it distributed? Where is this in the South Pole? And that's the question that Viper aims to address in this hunt for lunar volatiles. So if you are not aware of Viper, Viper is a rover mission, and this is it's a suite of science instruments that will go to the lunar poles and look at the water and other volatiles. We're going to look at the distribution and the physical state of the lunar volatiles, and we're going to map at a human scale. Right? This is why we want to go there. This is why we need the rover. We need to understand this at the human scale before we send the astronauts, as Dr. Lori Glaze was talking about this morning. Before we send the astronauts back there, we want to understand how these resources are distributed. All right, so we're talking about mapping on a human scale. What's the actual scale of Viper? So here on your right-hand side, you have a model of Viper with some of our team members. So you can see that Viper is about 1 to 1.5 human scale, depending on the human that you're using for scale. And then on the left-hand side, we have the Viper hardware. I literally 5 minutes ago got the approval that there were actual final pictures of the fully assembled rover, but I didn't dare try to go ahead and put them in my presentation. But this is nearing completion. The rover was assembled at Johnson Space Center, and it's getting ready for environmental testing. All right, so these are the specs for Viper. So Viper comes in at a slim 430 kilograms with a blazing top speed of 20 centimeters per second. And for a planetary mission, for a rover mission, that is actually very fast. Thank you very much. When we do prospecting, we're going to slow down to about 10 centimeters per second. And that's because we want to get increased science data. And so we need to go a little bit slower so we can get greater coverage. And I'll talk about that overall mission traverse in a little bit. We also have the capability to survive the lunar night, and we can withstand temperatures down to 40 Kelvin. And this is because we want to go into a permanently shadowed region and drill and understand how that water ice is distributed in that area. Right, so Viper is a suite of science instruments. So we start off with a neutron spectrometer. The neutron spectrometer provides hydrogen abundance and depth as we rove. And then we have a near infrared spectrometer, which we call NIRVIS. Everything has an acronym. So the near infrared information provides spectral data as well as temperature data. And then it also has an imaging capability. So it can image the surface of the lunar surface, the surface of the moon as we rove. Then we have M-SOLO, which is a mass spectrometer. The mass spectrometer measures gas phase measurements or gas phase molecules. So it can measure anything that is released from either the surface as we rove over it, or as we are doing some subsurface analysis. These 3 instruments here are always on and collecting data as we're roving and prospecting. Then when we decide we want to drill and do subsurface analysis, we have the Trident drill. So as we do this, the rover is positioned for maximum solar power. And then we go ahead and collect samples using the Trident drill. And this can collect samples from up to 1 meter depth. So the science team is very clever outside of me, and they are actually going to use the Trident drill in conjunction with the rover IMU to get subsurface sounding measurements. And then, of course, last but not least, we will use all the cameras that are on board the rover that are used for navigation. We will also be able to use that for some science capabilities. So all of these are working together to get the most science that we can out of our Lunar South Pole mission. So for the Viper instruments, I just want to say quickly that the NSS and the NERVIS and the M-SOLO instruments, they are led by NASA centers, but they have partnerships with commercial companies. And so this is just a list of some of the commercial companies that we're working with. And then the Trident drill is from Honeybee Robotics. They are no stranger to exploration either. But they were actually a part of a small business innovative research program, some of NASA's efforts to infuse small businesses and give them access to participate in space exploration. So as I mentioned, so Trident brings samples to the surface. Trident is an augering sample drill. So it will go down and collect bites of material. So it goes down and it collects these 10-centimeter bites, brings that sample up to the surface, and there is a brush that moves the cuttings from the auger to the surface of the moon. Doing so, kind of see here, creates this pile of regolith. So that's how we're going to do our subsurface sampling. When we create this pile, the NERVIS, the near infrared spectrometer, will take images, spectral data, and it will get a scene temperature to estimate the temperature of that. And then the M-SOLO mass spectrometer, that will measure any gas phase molecules that escape from the surface of the regolith as we're sampling. So you can see, together with the superficial measurements from NERVIS and the gas phase measurements from M-SOLO, we should have a complete picture of all of the volatiles that are there in that lunar sample. All right, so Viper, we are not going to find water. We are going to characterize different thermal environments. So the way that we have designed this is we have designated 4 ice stability regions. And you can see here to the right that this is an example of the 4 ISRs, ice stability regions, mapped onto the lunar surface. So the red color here is the permanently shadowed region, and that is thermally where the ice is thermally stable at the surface. And then around that, you have different thermal conditions, usually controlled by the topography of the surrounding area, where ice is stable either in the shallow or the deep area, but in that first meter. And then all this gray area is what we consider dry, because it's not, ice is not present within the first meter that we're going to sample. There we go. All right. So recent modeling by the Viper science team actually showed that if ice is present when we sample, we're going to find it in the first 85 centimeters of the lunar surface. And so what that did is it actually kind of redefined how we look at the shallow and the deep surface ice stability region. And so our shallow ice stability is anywhere from 0 to 20 centimeters. And then our deep ice is anywhere from 20 to 85 centimeters. So these maps were created with a lot of information and modeling, and we put this all together to help us define how we're going to execute the mission. Right, so Viper uses this information to create what we call science stations. And a science station is made up of predominantly one ice stability region, one ISR. So you can see here on the right, we have two science stations that are mainly in that light white colored, and that is in deep ice stability regions. And then we have two here in the dark, and that is in deep or shallow ice stability regions. So we also have one example that just went by to, I'm not going to go back to it. One sample in our PSR. So we're able to go into the PSR and then come back out. I'm going to speed through these next ones, but one thing I wanted to say was I have science-led exploration here. And after this morning, I wanted to save that or change that to science-driven exploration. And we all know that science and exploration work very closely together, and especially that happens in this mission. In the Mission Science Center, which is down here in the blue, we have instrument specialists and we have theme leads that are constantly looking at data and analyzing the data to understand how we can maximize any future objectives that we are going to reach and understand if we want to change anything in the future of our traverse plans. And you can see in the orange here, that is our Mission Operations Center where we're doing the driving. There are actually two science positions. And those two science positions in the mission operations, that's our conduit for injecting science into the real-time driver decision. So this is truly a science-driven mission. All right, and I'm just gonna speed through this a little bit. So this is an example of our science traverses that are not on a map. So you can see a little easier. We kind of, wiggle our way through a science station to maximize the amount of science that we're going to get. We go do about 3,500 meters of prospecting, and we have 3 drill sites. While all 3 of those drill sites are pre-planned, the third one is something that the science team can move based on what they find out with the first 2 samples. And so we do have some flexibility, but again, we're a solar mission. So we do have to make sure that our batteries are charged and we have to meet that safe haven on time. So there's a lot of things that go into making this happen. This is just an example of our mission area. And again, this is what we're going to explore for the first couple of days before we want to go into the PSR and get a sample from the inside of the PSR. So with that, I will say that the rover is 100% built. We are going into environmental testing and we are planned for launch and delivery in late 2024. Thank you.
Thank you. Okay, thank you. So we have time for a couple of questions at least. So please go ahead. Good questions.
This morning there were no
Thanks, that's very cool. Will M-Solo have the capability for isotopic measurements of the volatile species?
So M-Solo is a quadrupole mass spectrometer, which is not typically used for isotope information. What we can do is what we call bulk isotope differentiation. So we are looking at being able to differentiate large changes in isotopes. For instance, we should be, based on the data that we have, we can tell if the water is from solar wind implanted hydrogen and is deuterium free, or if the deuterium is something like what we would find, the ratio that we would find in the cometary sources. So we're not as good as Prospect is, because we're not meant to do that, but we're trying to stretch the capability as far as we can.
More?
Yeah, I'm really excited to see that you're going to be able to choose your third drill hole tactically. What sorts of data sets do you think you might use to make that decision? And is there a chance that you can go back to maybe an area you've already driven through to select it?
So we're going to use all the data that we have. every bit of it, right? So we are going to use the thermal data that Nervous is giving us along with all of the previous drill sites. And what's going to be really important, especially if we're not in a superficial area, is we want to understand how our data is correlating with models, because really we want to ground truth our models. And so if we need to go back to an area that is not, we can do that, but we still have to be able to make it to the next science station in time to not lose the light or lose the comm or anything else like that. So we do have to be somewhat strategic about it. So we are constantly in the Mission Science Center working with planners to kind of inject our science and say, what about this? Can we go here? How much time do we have? And we're actually doing a lot of mission sims. We need to do some more. And that's what we're doing as we come up. Now that we've delivered all the hardware, we really need to focus on how we gather all the data and make that decision and get that decision up to the drivers.